Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, 5 minutes late. So I'm very happy that Vijay De Silva is here. Just across the road, a bit of a long road from Oxford, but they try to make it a bit shorter. But he's going to talk to us about some recent stuff on characterisation and solving, and introduce conflicts along the way. Interrupt, go. Thanks, Vijay.
Thanks. So good morning. Thank you for not being on holiday. Apparently most of the lab and the department are at the moment. All right, this is joint work with Leopold Haller, who is another PhD student in Oxford. And it's also currently unpublished work, so I appreciate any feedback you can give me. My talk will be about abstractions that are already built into set solvers, so I'm not going to do anything new. I'm just going to take what exists out there and just explain it in a different language that I am familiar with. Right. So when I started my PhD,
Fingers.
Doesn't seem to like
old-fashioned.
All right. Yes. So when I started my PhD, my advisor was and is Daniel Koenig, and Daniel said, "What would you like to do?" And I said, I want to prove a really hard and important theorem, and it's going to give us a really efficient algorithm, and then we're going to implement this algorithm, and he looked at me, and he smiled. And then I was to learn the bitter truth. It's not that easy. But then I learned that there's actually a way to recover from your failure with some dignity. And that is to use the word lemma. So you try to prove something, and you don't quite get there, but you say, well, I proved a lemma. And actually, the mathematical process, to a large extent, is like that. You have this goal that you want to prove, and you don't often, if it's a sufficiently lofty goal, you don't directly get there. You prove a lot of little lemmas. And I would like you to hold this picture for, let's say, the next 3 or 4 slides in your mind. So there is a goal that we want to prove. We try to restrict that goal sufficiently so that we can prove an intermediate step. We call it a lemma. We try to generalize the lemma, and then we collect lots of different lemmas until we have a proof of the original theorem. All right. So blessed be the lemmas. Okay. The second part of the story is that my colleague Leopold Haller spent the summer of 2009 here in Cambridge. He was working with Satnam Singh. All right. So he was working with Satnam Singh on implementing SAT solvers on FPGA chips. All right. And after that, we shared the same office for about 2 years. So Leo came back, and I said, "What were you working on?" And he said, "What do you know about SAT solvers?" And I said, "I know lots of things about SAT solvers. I went to the Oxford Museum for the History of Computing, and I know that in 1869, William Stanley Jevons implemented the logic piano, which was the first SAT solver, and it could reason about 4 terms. And he wanted to extend it to 16 terms, but there wasn't enough space in his office." Yes. And Leo looked at me, and he smiled. He said, "Greetings from the future. In 2009, we can handle 100,000 variables." And this is not a joke. This is seriously something absolutely fascinating that has happened in the last 10 years. So starting about 1999, a combination of things has caused an exponential improvement in the performance of SAT solvers every year. And SAT is the classical NP-complete problem. So this has gone very much against what we would have expected from theoretical predictions. Okay. So why has this happened? Well, I don't know why, but what was behind it was an elegant algorithm, some really clever heuristics to implement the algorithm, and a lot of excellent nuts and bolts architecture-aware engineering. Okay? And it took all of this together with a consolidated research effort to make that happen. Now this talk is going to be about the algorithm. So one of the open questions posed in the survey that I was quoting was, can we take the lesson from SAT to other problem domains? And that would mean you need to lift the algorithm, You need to find the right heuristics and you need to find the right engineering. And in this talk, I'm only going to cover the algorithm, all right? So it's just conceptual. If you came here looking for I hope you're not too disappointed. So that was Leo's summer. Let me tell you briefly what this algorithm looks like. So if you recall the picture with proving theorems, well, the SAT solver will initially start and try to prove something. It will restrict the problem until it is able to prove a lemma. It will try to generalize the lemma, and then it will go back and repeat this process until it has a proof of the original formula. This procedure is called conflict-driven clause learning. So some people call it DPLL-based SAT solvers. The more technically correct term would be conflict-driven clause learning. It's what I will use here because there is actually a technical discussion with a difference between DPLL and we can come to it later if it's relevant. All right. So I need some technical terminology. We will have a set of truth values, true and false. There are propositional variables. A literal is a variable or its negation. A clause is a disjunction of literals. A formula in conjunctive normal form is a conjunction of clauses. All right. The two most important concepts we need are an assignment. An assignment assigns truth values to variables. And the satisfiability problem asks, given a formula, is it satisfiable? Right? But what we will do in practice is, given a formula, can we find a satisfying assignment? Slightly different, but that's what we will do. What does the algorithm look like? The first phase is called Boolean constraint propagation. We will start with a formula. And here is one of the key ideas. We only do very simple deduction. Okay? We will only deduce obvious information. So I want to satisfy this formula. What is absolutely obvious? Let's look at exactly the first thing in there. So if I want to satisfy this, x must be true. Okay? So I will write down the fact that x must be true. Given that I know x must be true, what can I now conclude if I look at the formula?
Not y. Replace all the x's with not y.
Yes. Well, I mean, if I replace all the x's, it's still not obvious. Well, I mean, in this case, there's only one. Yes, exactly. So not y must be true. In other words, y must be false. All right?
At which limits does the obviousness stop?
Go on. What do we do next?
We'll replace y, and now we just got.
So there's nothing obvious anymore, right?
So obvious means a single variable in a conjunct.
Exactly.
That's what you
so
mean by
what does obvious mean? This thing that I'm building here is called a partial assignment. It's a partial function from variables to values. This obvious rule that I was applying is called the unit rule, which says if all but one literals in a clause are false, then the remaining literal must be true. Okay, that's what obvious means. The Boolean constraint propagation step says repeatedly apply this rule. All right. We have already seen that if we think of it as a deduction rule, it's incomplete because sometimes I cannot go further. Right. So that's Boolean constraint propagation. What do we do when we are stuck? We try to narrow the problem down. We make a decision. What is a decision? It's an assumption. We say assume that Z is false. So now what happens? So we know that X must be true, Y must be false. Suppose Z is false.
Not false.
Exactly. So if you look at this clause, we will say, right, Y is false, Z is false. So not W must be true. In other words, W must be false. So then say W must be false. But, what happened to the last clause? So if you look at the last clause, Y is false, Z is false, W is false. I cannot satisfy that clause. I have what is called a conflict. Okay. Now, what will happen? We say, we have proved that if I assume Z is false, then the formula is not satisfiable. This is like a lemma. Or we're not at the stage where we have a lemma yet. We would like to extract information from this proof that we've done that we can reuse. That would be the lemma. So we will learn something. I will come back to learning later. For the moment, assume that there's a black box that tells me the conflict happens because this formula is unsatisfiable. So my original formula, in conjunction with X and not Z, is unsatisfiable. Okay. Suppose there's just a black box that tells me this. We will come back to the black box later. So what can I conclude? I can conclude that for phi to be satisfiable, I can add the conjunction of the negation of this formula, and it will still be satisfiable, right? If it's satisfiable. Because it's not satisfiable under this restriction. Go on.
Wait, where did y go? Y was as well. So shouldn't it be x and y and not z?
No, something just told me this.
Oh,
So don't worry about deriving it. We will come back to that later.
Is it
Okay.
even
So
true?
somebody just says to me, this formula is unsatisfiable based on what you did before. Let's not worry too much about where that came from. I will show you, right? But it's only relevant for the second half of the talk. Suppose that happens. Since this is unsatisfiable, we know that I can negate this and add this there. And that's what we will do, all right? I can add this back there. So this is like the lemma that I have added. And now we backtrack. So what happened? We derived a conflict in the presence of an assumption, right? There was information I derived before that. I need to go back to the point where I made the assumption and do my reasoning again. All right. This is extremely important. If you were doing a mathematical proof, what would be something very natural to do at this point? I assume that Z is false, and I prove the formula is unsatisfiable.
Try Z is true.
Exactly, try Z is true. This is not what a set solver does, okay? This is extremely important. This would be case-based reasoning. Try X, try not X. A set solver does not do case-based reasoning. This is extremely important to appreciate. So this is the most crucial heart and soul part of the set solver.
Choosing Z equals false, that was already case-based reasoning, wasn't it?
That was part of it, but to complete the proof,
That's it.
what I mean by if you do a case-based proof,
Uh-huh.
you would have a set of cases
That's it,
done.
right.
Right? So yes, you try one case, and we learned the lemma, we added the lemma back. So let's go back to doing obvious reasoning. So what happens now? Everything I did till this point is valid.
Okay. That was just Boolean constraint propagation. Now you've added a new clause.
Yes.
So now you
So
make
now I can do
PCP
Boolean
make
constraint
it further.
propagation again because I might have more information in the clause.
So now you know Z must be true.
And now I know, because I have a clause that only contains 2, and I know that Z is false, I know that Z must be true. Okay?
Mhm.
So it's very important to note that I did not do a branching-based reasoning here. I learned a lemma, and this lemma could trigger at multiple points in the future, right? And there could be things in this lemma that trigger not related to Z being true or false, right? It could be that I learn a bigger lemma and there. So this is very, very important. So it's really the idea that you have lemmas floating around that you can reuse, right?
Could the lemma have been Z must be false?
Yes, the lemma could very well have been Z
Could
must
have
be
been
false,
that.
yes.
You got a better one by the magic box.
So actually in this case, in my example, Z must be false would even be better than what I used, but I wanted to use that too. I would have to pick a bigger formula to show you, and I will show you later
Okay.
a larger formula. All right. So there are several interesting things here. We search for an assignment, and we do some deduction. Building the partial assignment, this is a model theoretic proof procedure. Learning lemmas, this is proof theoretic. Okay? So there's a model theoretic and a proof theoretic search procedure that are feeding off each other. Okay? This is really at the heart and soul of this algorithm. And the point of emphasize, in case I forgot to mention, it's not reasoning by case splits, okay? Because this is a common misconception that's out there. So that was Leo's summer of 2009. What did I do in 2009? Well, I also interned in Microsoft herself. Surprise, surprise. With Aditya Nouri, who's in the audience in India. So Aditya was working on a program verifier, and he said to me, right, so I have some problems in my program verifier. Can you use your abstract interpretation to solve this? And I said, So I said, suppose we didn't have any integers, and definitely no dynamically allocated data, and preferably no loops in the program, no recursion. And Aditya looked at me, and he smiled. But this is not a completely pointless exercise. So what kind of program could you write if you made all these restrictions? Well, you could write something like this. So I didn't throw out conditionals. So assume you have Boolean variables, and you could write assertions. Assume that the Boolean variables are initialized to arbitrary values. Now I ask you, is the assertion violated in this program?
Well,
Depends.
if there's a satisfying substitution for the Booleans.
Exactly. So this program is safe if and only if the formula is unsatisfiable, right? But now we can think about it as a program verification problem. I say, all right, I know program verification. How can we use all this existing program verification technology to think about the problem? In particular, I would like to use abstract interpretation. What is abstract interpretation? In their own words, some of the most eloquent lines, in my opinion, written in a programming languages paper, A program denotes computation in some universe of objects. In other words, we have a trajectory in some space. And the meaning of the program is the limit of this trajectory. Technical term, it's a fixed point, right? What is abstract interpretation? We take this trajectory and we evaluate it in some other space of abstract objects. And then we will compute an abstract limit. And the soundness proof will tell you that this abstract limit will over-approximate what you had initially. So the first object we need is a concrete domain. So we have programs, we have variables map to values. These are called environments. Okay? So the domain consists of sets of environments. So this is what an environment looks like. Assume that I have two variables, P and Q. P has the value true, Q has the value false. Okay, so let me write the set P contains those environments in which the variable P is true. The set Q contains those environments in which the variable Q is true. Okay? Now I can build a power set of all environments. I have no environments here. I have all environments in my program here. I have the environment P, Q, P, and Q, and so on. This is very standard. Okay? So programming language is 101. Suppose I have a statement, assume not P or Q. Right? And I ask, what is the strongest postcondition of this statement? So suppose I have the set of all environments, and I have this statement. What would be the strongest postcondition? It would contain the environments that satisfy the formula, and that would be, yes, not P union Q. Okay? But I can ask, strongest postcondition with respect to an arbitrary formula. So I say, suppose I have the strongest postcondition with respect to P. Well, the P and Q being false will not satisfy this. The only thing I will get is that P must be true and Q must be true. So the strongest postcondition of P will be the set P intersection Q. Question: what are the colored boxes in the picture? Bonus question. All right. What happens if I apply the strongest postcondition to any of these boxes?
Maybe they're invariants or something? No.
Yeah, so suppose I have P and Q. Well, that's actually containing all assignments that satisfy this, and if I take the strongest postcondition, I will remain here. Suppose I have Q. Well, everything in Q satisfies the formula. The strongest postcondition will be this set. So these are the fixed points of the strongest postcondition. Okay? And Tarski's theorem tells us, as you can see, that they also form a complete lattice. I have the greatest and the least fixed point. Okay, so more or less, this is what we saw. We have the concrete domain containing environments. We have the strongest postcondition. You can define it over predicates. As a predicate transform, you can just define it over states. The following are equivalent. The formula is satisfiable if and only if the strongest postcondition, I will write phi here for the assume phi statement. The strongest postcondition of this is not the empty set. If and only if the greatest fixed point of this is not the empty set, because the formula is satisfiable as a non-empty set of satisfying assignments as a non-empty larger set of satisfying assignments. Okay? So we've done the first step of abstract interpretation. We've taken the semantics of our program, we've characterized it as a fixed point. Now we need to abstract the program. So what is the standard thing you do in abstract interpretation? Instead of this lattice or this space, we will have a different lattice, a different space, okay? So here I will consider only P, Q, not P, not Q, and I will close them under conjunction. This is a standard abstraction that is called the Cartesian abstraction. Instead of the power set of environments, I only have individual environments, but I change my value domain to be sets of values. So here I have that the variable P is true. Here I have that Q is true. Here I have that P is true and Q is true. You see that all of these can be written as a single environment where values are sets. What I cannot do is express disjunction. So here I have P and I have Q and I have P or Q. P or Q does not live in this lattice. So it will be over-approximated by the value top, which is the maximal element. So now we can ask the question, what is the strongest postcondition for the assume statement? Right? So I will work it out. We will see some examples. But the standard example would be, I have something like this, and we see that this would be the strongest postcondition in the concrete world, but if I abstract it, I will get top. So we see that the abstract semantics will have more environments than the concrete semantics. Okay. So what happened? This is the concrete domain, containing sets of environments. The abstract domain contains the Cartesian abstraction. It's well known that there is a Galois connection between these two. That means I have an abstraction function mapping sets of environments to the unique environment that over-approximates all of these. In abstract interpretation, there's the notion of a best abstract transformer, which says that if you want to get the best result that you can do in the abstract, you take your set of abstract environments, you go to the concrete, you compute the strongest postcondition there, and you come back to the abstract. Okay? But there's a problem with this, because suppose I were to evaluate it in this manner. Suppose I take top in the abstract, I will come to top in the concrete, I will apply the postcondition. That involves computing the satisfiability of the formula. Okay? So in general, we almost never use best abstract transformers, because it's satisfiability hard or as hard as whatever problem you want to solve. So what we will do is we will use the disjunction, instead of disjunction and conjunction, we will use the join and the meet. We will only live in the abstraction. We will never touch the concrete world, because this connection is expensive. Okay? And there is a standard soundness result saying if you compute a fixed point in the abstract, then one direction is true. If I get bottom, then the formula is unsatisfiable. But there may be formulas that are satisfiable in the abstract but not in the concrete. Let's look at an example. So I have P and P implies Q. Okay? Standard thing. You know that this would give us P and Q. I will write this environment where P is true and Q has arbitrary value. That's the environment P goes to true. So what is the abstract strongest postcondition of top? Right? So now let's evaluate this in a compositional manner.
Wait, this is so if you start top meaning I know nothing.
Yes.
And you go past assume phi.
Yes.
Then what do you know? Is that
Yes, exactly.
in the abstract world?
Yes, yes. So
And this particular abstraction is this Cartesian one.
yes.
Okay.
So I thought that object would be called the strongest postcondition, right? If I have something and I go past this, what do I?
I was just checking that I
Okay,
didn't miss
that's fine.
anything, does it?
Okay, so exactly. But the only difference is we do this in the abstract world. So we say that P is true because I know that P holds. And if I have top and not P, then I know that P is false. And the same holds here. Right? What happens when I take the join? Well, I cannot express a disjunction precisely. So the join will give me top. And that means this will just give me top. And I will not work it out. I mean, it's very easy to see that in the concrete world, you will get P is true and Q is false. Sorry. P is true and Q is true. This is a mistake. P is true and Q is true. This is what I will get in the concrete. And we see that the two are not the same. I have lost precision by computing the strongest postcondition in the abstract. Happy? Good. All right.
That's what abstraction does for you, right?
Yes, that's what abstraction does for you. However, there was a fixed point that we haven't evaluated yet. Right? So there was the greatest fixed point in the concrete, right? Because I said, if you take the strongest postcondition, you will get a set of assignments. And if you start with true, you will actually get the set of all satisfying assignments. And you cannot reduce this set anymore because if you're there, you will stay there. So this is the greatest fixed point. So we can evaluate the greatest fixed point in the abstract as well.
Wait, you only need fixed points if you've got a loop or something, right?
No, you don't.
You've just got
Yes,
straight
you
line
only
code, you
need
don't need fixed point at all.
But, sorry?
If you've just got straight line code, then you don't need to take a fixed
You
point.
don't need fixed points, no. But
And even if you've got straight line code, wouldn't it be wrong to take a fixed point? That would mean
it depends on how you define the fixed point.
Oh.
That's why I'm defining greatest fixed point. There is in fact a theorem of Couzeau and Couzeau saying that suppose you have a concrete transformer and an abstract transformer, then soundness guarantees that the result you compute in the abstract is above the result you compute in the concrete. And then if you appropriately define the transformer, you can compute a greatest fixed point in the abstract, meaning I will have lower iteration, such that it always remains above the concrete. Right? So you start with the initial value as the top thing that you will have, and you come down, remain above.
I think what I'm confused about is that if I have a program that has a bit of straight line code and then a loop and then a bit more straight line code and then a loop, well then I need to do a transformer, then a fixed point computation, then a bit more transform, another fixed point. It's not just a question of doing one transformer and then a grand fixed point across the whole thing, is it?
So what would be the analogy in your case? I don't have loops, right? And I'm wrapping the whole thing inside a greatest fixed point. In your case, we would say, we have a transformer, we compute a least fixed point, we have a transformer, we compute a least fixed point.
I see.
You plug this whole thing back in again and do a greatest fixed point.
I see. So you're just thinking of programs that consist of some straight line code with a loop around the outside. Okay.
No, that's not what I'm doing.
Oh.
Because then you would compute a least fixed point.
Oh, okay.
in which case what I'm doing would be to wrap a greatest fixed point around your least fixed point.
So why are you doing the greatest fixed point at all? If you just got straight line code, you don't need to do it.
I don't need to do it, no. But
So
it
why
improves my
are you doing
precision.
it? Why
It
is this
improves my
idea?
precision. So you can prove this result that if you have a concrete value and an abstract value,
Yeah.
right, and you apply the transformers, then you're guaranteed to over-approximate it. And then if you repeatedly apply the transformer in the abstract without taking joins or so, you try to come from top, then you are guaranteed to stay above this value but have a more precise value. So you can get a decreasing sequence of iterates whose limit is still above the concrete value. And this is a way to improve precision necessarily in the abstract. But for now, we don't even need to understand that. All I would say is, I characterize satisfiability as a fixed point. An abstract interpretation tells me, well, you want to approximate this, just evaluate the same fixed point in the abstract. So I did that. I mean, it doesn't even have to have an intuitive explanation in these terms, right? No, what I mean is, if you generally want to look at this as a problem-solving strategy, you don't have to say, oh, what does it mean for this to be a program? You can take any problem in any space. It doesn't have to be a program verification problem. I set it up that way. Okay, but so we weren't done here, but do you see now that if I have, so actually we will see the precision improvement here. If I just apply the transformer, I would lose precision. But now I apply the strongest post-condition to this again, right? If I had a least fixed point, I would be taking a join, but I compute a greatest fixed point, so I just wrap it around itself again. So I will have not, what is the strongest post-condition of P being true, assuming not P? Well, it would be false, which is bottom in the abstract, so I will get bottom. What is the strongest fixed point, its strongest post-condition of Q, assuming P goes to true? Well, I will get that P is true and Q is true. And join with bottom would give me this, meet this would give me this. And we see that by iterating in the abstract, I have improved my precision. So okay. Simon Peyton-Jones, yes.
Yep.
May I call you Simon Peyton-Jones?
Indeed, yes.
I can call you John if you prefer. All right, so the point is, and we see the demonstration here that you lose precision in the abstract, but because of the way fixed points behave, you can iterate something different in the abstract and improve your precision, all right? Okay, so that's basically, we've been over it now a lot. I won't go over this. Essentially, we said we have a fixed point, evaluate the abstract fixed point. And it's sound but not precise. All right.
So I have a question.
Yes, go on.
So I guess the question is, why do you have the programs in the first place if you have assume and what's the other one? Assert, assume and assert.
Presentation.
Oh, okay. So it's not to do with like BDDs and branching programs or anything?
No, there's nothing fundamental about it. You can also just think about it as abstracting the semantics of programs.
Okay.
But if you do it this way, it's very obvious that what you're doing is strongest post-condition computation.
Mm-hmm.
And then you can use a lot of intuition from what has been developed in program analysis because that's the technology I want to apply. So Leo came back from his internship, I came back from my internship. Unfortunately for everybody in our group, we were in the same office. And then we talked. And then we talked some more. And we were like, oh, really? That's really cool. And this is really cool. And then we were talking and talking. It was getting worse. And I said, oh no, SAT abstract interpretation, SAT blah, blah, blah. And then we ran to Daniel's office one day and he said, oh, Daniel, SAT abstract interpretation, SAT and this and that. And we were going back and forth and back and forth. And then Daniel said, hey guys, just cool down, yeah? So can you give me a clear summary of what you're saying? Okay. Okay. A SAT solver and an abstract interpreter walk into a bar. And Daniel said, is this some kind of joke? All right. But let me show you the inside of a SAT solver. This is a well-known SAT solver. It's called MiniSat version 2.2. There are a few things to note here. The solver has a state. Okay? The solver can be okay, it's happy, or it can be in conflict. All right? If this Boolean value is false. It contains a vector of assignments. The size of the vector is just the number of variables that you have. Okay? A variable has three states. So L-bool is up here, you can see. It can be true, it can be false, or it can be undefined.
So
I
that's
have
that
a
little
question,
partial
sorry.
assignment. That's the little partial assignment thing you had earlier.
Yes, exactly. So
So
this is
excellent.
implemented. So I swapped two things, right? I did SAT, I did abstract interpretation. I'm going back to SAT.
Okay. Yeah.
Actually, I forgot to say something. Question. We evaluated this greatest fixed point here. Did anybody see anything vaguely familiar happening? So I have this formula here. In the first step, I conclude that P is true from this formula. Let's just look at the results again. In the all right.
Don't assume just Mr. Dimitrios has realised it. Everybody else has. He's a very clever fellow.
I'm going to tell you, don't worry. All right, so, I mean, the solver can be conflicting. A variable can be true, false, or undefined. This is a standard information ordering. I can further define an order on partial assignments, which is the most natural order. If I have an assignment and I extend it, then this assignment is less than the other one. It's the standard information ordering. What is the ordering on the Cartesian abstraction? A variable is a set containing true, false, and a set of Boolean values. There is an order isomorphism between these two. Partial assignments are Cartesian abstract elements. The unit rule says, given a clause and a partial assignment, if every literal is made false by the partial assignment, you have a conflict, right? Otherwise, you make the remaining literal true if all but one are false. Otherwise, you do nothing. I showed you intuitively that this is what the abstract strongest post condition is doing. So in fact, if you take the order isomorphism that we defined before, it's going to commute with the unit rule and the abstract strongest post condition, right? So I apply the unit rule to a partial assignment and a clause. I apply the isomorphism that I have. I will get the same result if I take the partial assignment, go to the Cartesian abstraction, apply the abstract strongest post condition there. The question? So the unit rule.
Wait. You conflict if pi makes all literals in phi false. I thought a literal was x and not x. Do you mean all clauses?
No, it makes all, because a formula is a conjunction of clauses.
Yes.
So if I cannot satisfy any literal in the formula, in a clause.
So you're taking a whole formula phi.
No, I take a
multiple
clause
clauses
phi.
and-
I take a clause phi.
Phi is a clause. Beg its
I'm going to do this
pardon. Sorry, I thought this
compositionally.
was the whole formula. Beg its
No,
pardon.
it's a clause.
Okay. Okay.
But I build up the transformers for formulae from transformers for
Okay.
clauses.
So I was one level out.
It's fine. But the next level is formulae. So I could show you the code, but because the code is meant to be highly efficient in terms of scheduling, there's a lot more going on in selection of variables and which clause you should apply the unit rule to. But more or less, if you look at any survey paper or any tutorial, it will tell you that the Boolean constraint propagation step looks like this. You start with a partial assignment and a formula. And now we pick a clause in the formula and apply the unit rule, right?
Mhm.
And then we repeatedly do this. Well, what is this? We start initially with an assignment where everything is empty. We apply, So where you know nothing, which is the top value, apply the unit rule, apply the unit rule, apply the unit rule, you will get a descending chain. This is the greatest fixed point. So the Boolean constraint propagation step is greatest fixed point of Cartesian abstract transformers. Okay, and this is like up to order isomorphism, so I'm not drawing an analogy here, it's something you can prove. All right.
So when you added the extra clause, the lemma that you learned, did you change the class of satisfying assignments at all? Or did you shrink it? Or does it say the same, or did you shrink or grow? When you added that extra clause.
No, I didn't change the class of satisfying
So the
assignments.
class of, so you're not changing the class of, you're not
So we can
changing
think
the
of it as a
satisfying
semantics
assignments.
preserving
Right,
transformation.
so it's complete. Okay, so then the sort of syntax is changing. We're iterating towards a sort of syntactic fixed point, but the semantics isn't changing at all.
You're
I
jumping
like
ahead of
abstract
me, yes.
interpretation.
So we can think of this as the anatomy of an abstract interpreter. I want to show you an abstract interpreter because I showed you a Satsal word. Now I can say, well, you don't have to look very far. I've already shown you an abstract interpreter. But now comes your question. So what was all the learning business? Let me show you a bit more about how learning works. So this is meant to be more special effects, all right? So let's not try to understand it too carefully. We can come back to it, but there are one or two things I want to say within the time that we have. Apparently, the fire alarm is going to go off if I run over time. I would not like that. All right. So I will just work this out for you. I hope you will believe me. We can check it later. So I mean, the initial part is easy. Okay, so there's one more piece of terminology I need here. The DL0, this is called decision level 0 in the SAT solver. It means I have made no assumptions. Okay, so I can conclude something, not making any assumptions. When I make an assumption, that's decision level 1. So I'm going to stack up my assumptions to know how deep I am into my, how many assumptions have I made. So now if I have 1 and 2 in the formula, I can conclude that 3 must be false. Right? So again, I'm going to go over this fast, not worrying, just believe me that...
So that was BCP?
Yes, this is a BCP
Okay.
step.
And the DL steps are when you make an assumption?
Yes, exactly.
Okay, that you may have to undo.
Yes.
Okay.
So what are we doing here? We are effectively logging our BCP behavior. We're saying you knew this and you knew this, so you did this. And we're logging the decisions as well. So we build a graph-like log. Okay? At some point we reach a conflict. So what we know is I followed this sequence of deductions and I reached a conflict. All right? Here's a very nice idea, which is if I make a cut in this graph, right, it will tell me that these are the assumptions you needed, or these are the facts that must be true to derive a conflict. If I make a cut that disconnects the roots from the conflict. Okay? Because you know that if I start from all these facts, I can derive a conflict. This much we know. But in fact, I could move that line anywhere as long as I disconnect the roots from the conflict. And I will know that if everything in this cut is true, then I have a conflict. Okay? So what can I do? I can take everything I have in the cut. Their conjunction would give me a conflict. I can negate it. I will get a clause. So this is the mechanism behind the lemma learning. Yes, please.
I'm sorry, what do you mean by cut here? Okay. So this dashed line corresponds to a particular formula.
Yes, so every cut...
In what way?
In what way?
Yeah.
You read what is coming into the cut. So here I have not 9 and not 3. I write it in here. This is a sufficient condition for a conflict, which means if I add not of this sufficient condition...
Okay, yeah. Thank you.
Right? So I can add the negation of any of these as a lemma that I learned. Which one do I choose? This is a heuristic process. There's actually a deeper reason inside here. So I explained the whole solving mechanism as strongest postconditions and abstract strongest postconditions, right? We can think instead of weakest preconditions. I want to know if a formula is satisfiable. I can also ask, is my formula unsatisfiable? I can ask, what is the weakest precondition with respect to false of the assumed statement? And if the weakest precondition is true, then the formula is unsatisfiable, right? The weakest precondition is anything else, then I know that only these values will not satisfy everything else. I can play the same game. I can then go to an abstract domain and I can compute abstract weakest precondition. But there is a problem here, or there's a difference here. We need to under-approximate weakest precondition because I know from this you can satisfy it. So we shouldn't over-approximate that because we might conclude formula are satisfiable, which are not. So I was using over-approximating abstractions combined with strongest postconditions, or you can use under-approximating abstractions combined with weakest preconditions. The problem is, if you have a distributive abstraction, meaning the lattice that you have is distributive, you can represent both abstract strongest postconditions and weakest preconditions, which are sound. But we don't have a distributive lattice, so you can only do one. So the weakest precondition will necessarily be heuristically under-approximated. So this learning part can be viewed as a heuristic implementation of an under-approximating weakest precondition. That's really what we're doing. We're saying, this is what I learned. I derive the conflict. So the ideal lemma that I would learn from my conflict is just weakest precondition of false from that conflict, which would tell me what brought you here. But there is no uniquely defined weakest precondition in the abstraction. So we take this graph and we cut it and we do all of this.
So, a very simple cut is the one right at the left. Right, it says
This.
2, 4, and 6.
Yeah.
And those are just the assumptions. They can't. That set of assumptions can't simultaneously. Why did you just choose that? Why did you go with all this stuff about cuts? Why do you choose 9 or 3 rather than 2, 4, and 6?
There might be very small cuts, which are, so I mean here I will get a big clause and there might be, so instead of 9, if I have something like this, then heuristically this is So first it's smaller, it takes less space, but also it might prune your search space more if you have a smaller clause. So it's part of the generalization idea. So this, if you just took the cut from there, that would be really case-based reasoning, right? You say, I assume all of this, I must take the negation.
I see. So you're saying that
So somehow inside this graph, you heuristically try to say, what was only necessary for doing this?
So you say the stuff and is the intuition as far to the right in this graph as possible? The rightmost cut on the screen?
Is it? So Christoph would know more about this.
Uh,
There are many heuristics. I don't know.
There are many different heuristics, and they tend towards the right. Yeah,
Ah.
but all the way to the right is also not the best.
So I think what you would like is to minimize the number of nodes in your cut. That's what you would really like.
Yeah.
You would like as small a reason as possible for the conflict, right?
Oh, so I see. So you might have a few things, and then it goes all bushy and then gets...
Yes.
Exactly.
So the graph is not always going to look like a cone.
Because you want the most reusable lemma that you can find. And that sort of depends on the rest of the formula as well, as how far.
So to go back to what you were saying, here's the abstract interpretation analogy. Suppose I have a program like this and this is my abstraction. Right? I will go over this rather quickly. I want to show that this assertion holds. If I go down this branch, I can show that x is greater than 0. If I go down the other branch, I can show that x is less than 0. But I will come here and I have a joint that will get that top. And then top meet this is not bottom. So in the abstraction, I will believe that there is the possibility the assertion can be violated. I can rewrite the program like this to move the assertion inside. Here's a semantics preserving transformation. But now, if I run it in this abstraction, this is exactly what you were saying, right? I have changed. So isn't this what, well, maybe not exactly, but you were commenting on the fact that I'm changing the syntax of the input problem. And this is a pretty significant point that sometimes if you change the structure of your program, you can use the same analyzer to prove more. I have not endowed my analyzer with any more reasoning power, but I have made the effort to structure my program in a way that's more analyzer friendly.
Well, and there's only one way to have less joins.
Given this program and this abstraction, yes. But if you have, certain kind of multiplication and you're over-approximating them with, say, intervals or so, then it could be that you split on values, and this would be, so it's not just less joins.
Okay.
And when you're in a loop, then,
Yeah.
I guess also
it's more technical. Okay, so where have you seen this before? Well, I want to analyze this program. I say, well, I try to analyze it using Boolean constraint propagation, which is a standard abstract interpretation. I learn a clause, and then I go back here. And this is a big difference to what we had before. It's not case-based reasoning because I'm not doing if blah, else blah. Right? This is the difference. But it still sits within this framework of trace partitioning, which is the technical term for what I showed you before. So, to summarize...
Why have you moved to assert rather than assume? Some slides have asserts on, some have assumes.
So the assume is the way I write the if condition. So if would be assume phi, assume not phi. And the assert is always just the assert. It's just, I don't even need this. I could say, can you reach this location? It's just to pose it as a black box safety problem for a black box analyzer. All right, so to summarize, we have seen that there is a one-to-one mapping. The partial assignments are Cartesian abstract elements. The unit rule is the abstract transform. So on. There's one thing slightly dissatisfying here. I showed you all this business with the graph and so on. None of that was required for me to explain the analogy to trace partition, right? Because I could have just said at the point that you asked me, yeah, look, there are some times when we transform a program to make the analysis perform better. What are we doing? We're transforming a formula to make the analysis perform better. So it's more or less satisfiability solving and program analysis people are doing the same thing in different guises. I didn't need to go into the whole story of the graphs. Okay, so if you just want one slogan to remember, we know that the conflict-driven clause learning algorithm combines partial assignments, PCP, and learning. If you're a program analysis person, you can just think of Cartesian abstractions, fixed points, and trace partition. All right.
So if I was a program analysis person, wouldn't it? Maybe I should say, there are two things you might get out of this. Either you might say, oh, program analysis people should just transform their problems into SAT problems and give them to SAT solvers. Or another thing you might do is to say, oh, using these insights, I could build a better abstract interpreter or perhaps a better SAT solver. So which of the two are you?
Yeah, so I mean, I'm actually not advocating either. I said, here's something beautiful, and there is some cosmic joke in here, okay? It's that there's a lot of dissatisfaction with the state of the art of program analysis tools, or some people are quite unhappy. They say, oh, but then there are these really efficient SMT solvers and SAT solvers, right? And there's a big move, if you look at papers being published, to heavily exploit SMT solvers and SAT solvers to implement program verifiers and static analyzers. And here's the deep irony. What are satisfiability people doing and SMT people doing? They have been implementing solvers which are heart and soul abstract interpreters, essentially static analyzers, right? So we run away there, and deep inside this new technology that I want to use.
It's like money laundering. You can use Kuzo without admitting it.
Thank you. I shall remember that technology for the next time.
So good. Go ahead. I mean, you're saying that's a good thing.
Yeah.
Right?
So,
it's a kind of insight, but the story remains the same. It's a good plan to reuse that for that engineering work.
Plan. I mean, in fact, I shall come back to this point at the end. I have a few minutes. I want to quickly, so if you read that, that's fine. If not, it's okay. I want to tell you one more thing. So the graph is relevant. The next bit is going to be quite different from everything else I told you. It's just a high-level picture of something. Okay? And I'm going to go all the way back. I went to 1869 for the first SAT solver. I could go even back. I could go all the way back to Aristotle, but I won't. Okay? So in the 1800s, George Boole tried to formalize, and was the first person to formalize modern logic as we know it. So what did he do? He gave logic an algebraic semantics. That's why we have the term Boolean algebra. He said conjunction and disjunction are algebraic operations, right? And propositions live in some algebra, right? Later, Cantor invented set theory, and Frege based the predicate calculus on set theory, and then you had Russell and Whitehead doing the Principia Mathematica and all of that. And to a large extent, our conception of logic has come from them, okay? But the algebraic view was around as well. Now, if you're acutely aware of these two things, that you can do logic via algebra or logic via sets and relations, then there is a very disturbing question that comes up. Am I doing the same logical thing in both universes? Am I going to conclude the same things? Meaning, if I prove things about my logic using an algebraic semantics, am I going to prove the same things using a sets and relation-based semantics, right? And the answer was initially for a special case given by Tarski, who also credits Lindenbaum in his paper, that the complete atomic Boolean algebras are power set lattices. Okay? So if you have complete atomic Boolean algebras giving you semantics here, you can think in terms of sets. But there are Boolean algebras that are not complete. So what happens? The answer was given by Marshall Stone, who said you must always topologize, and he used topology to show any Boolean algebra can be represented in terms of sets. This is perfect. Okay, so let me give you an example. You can continue this for modal logic as well, and that's where I will draw an example from. Here is a Kripke structure, right? I have three states which have transitions, state label P, Q, P. I can think instead in terms of logical formulae. I have the formula false, which is satisfied by no state. I have the formula P, which is satisfied by these two states, and next Q, which is not satisfied by this state because it has no outgoing transition. It's only satisfied by this state, P and next Q. So this formula represents this state, or can be thought of as representing this state. The formula Q is only satisfied by the state 2, so I have Q. The formula, all my successors are false, meaning I have no successors, is only satisfied by this. So I have formulae that can represent my transition system. Instead, if I didn't show you any of this, I could just show you the algebra. And I could say, well, we have three elements, 1, 2, 3 in the algebra. If I have the element 3, then I know that the predecessor of 3 is 2. So I know that in the transition system, there must be an edge from 2 to 3. The predecessor of 2 is 1, 2. So there is an edge from 1 to 2 and 2 to 2. All right? This would be the algebraic semantics of this logic. Another way to look at it is it's an algebraic description of the transition system. So I have logic, I have algebra, I have relations. Okay? And I can basically move between them. These are three different worlds. And this is a very long story starting from Johnson and Tarski in 1952, and it continues till today because you can say, well, what about logic without negation? So I have a positive logic, and then what if I have substructural logics, which don't have all your classical properties. So then you're interested in having algebraic and relational semantics, and you're interested in now they're the same, and you can ask these questions. Right, so we have algebra, logic, and relations. What is a specific example of an algebra? Well, it's a lattice. That's what we've been seeing. What's a specific example of a graph? Of a relation? Well, a graph is a representation of a relation. I've been talking for about 40 minutes, 50 minutes now. What lattices have we seen? What's an example of a lattice that we saw today that I used a lot?
Environments.
Environments or abstract environments, Cartesian abstraction. What's an example of a graph that I had?
Conflict graph.
The conflict graph. And the formula we were learning were clauses. So we can take this loop and rewrite it. And amazingly enough, you can apply the representation theorem. And you will start from a lattice. You will derive a graph-based representation of a lattice, which is more or less the information contained in your implication graph. From an implication graph, you can go to the logic, which you can just do in this. You can go back. So mathematically, these things represent in some way the same information content, right? What's amazing is that algorithmically there is a difference. If I give you a lattice, what's the most natural thing you can do? You can compute a fixed point in a complete lattice anyway. If I give you a graph, what's the most natural thing you can do? You can find paths, you can take cuts. That's what we do. If I give you a formula, well, you can write down logical statements as formulae, right? So the funny thing is I have, in some sense, equivalent mathematical representations of objects, but they're fundamentally algorithmically different. And I can do things by translating between these universes. And, this was... So, to go back to the question I started off with, can we take the lessons of SAT solvers to other domains? Well, what we have seen, I haven't shown you how to actually go there, but I hope you believe me that the road is to some extent clear. So instead of partial assignments, I can swap in any abstract domain. To come back to your point, because there's a lot of domain-specific knowledge in there. How do you build a really efficient fixed point iteration? How do you select variables heuristically? Because these are all things that make things really efficient. Instead of the unit rule, I can have an abstract transformer. BCP would be the greatest fixed point iteration. I haven't gone into this too much, but basically the representation will give you these kind of ideas. What is the right generalization of decisions? Well, we decided P or Q, right? So the P or Q were the top elements just below, in my lattice, just below the top element. So they're called the meet irreducibles. I cannot get them by taking any two meets in the lattice. Those would be my decisions. And so on.
So the stuff I'm taking away now is that the SAT solver is a kind of special case of the abstract interpreter thing. You may take ideas from SAT solver technology and apply them in the more general setting to get abstract interpreters that are somehow better than anything that's been done so far.
Absolutely. Cool. So where I was starting from was here, where I have nothing very complicated, and the conflict-driven closed learning algorithm lives here. Propositions. I can add in graphs, and I can get transition systems. We analyze these in finite state model checking, right? We can think of them as programs with no data. I can go into the logical world, where I have a first-order logical theory or something even higher order. So I combine data and control, I will get programs, right? So somehow, to me, what the SATs, what I would like to say is now, based on these insights, we can take this technology and try to move it to the other domains and do something significant there. To put it a different way, so imagine there was this world, right, where you didn't have all the complications of programs. Imagine programs were extremely simple, and you wanted to first build a compiler that could verify your extremely simple program before you introduced a new programming language construct. And imagine you start with only booleans and conditionals. Then what would this amazing compiler look like, or program verifier look like? It would look like a SAT solver, right? Now assume the other thing, you have all this algebra and logic and it's sitting in some great harmony in mathematics, but you say, well, you should derive algorithms from this. We have representation theorems between different universes. Well, take these objects, perform algorithmic computations on them, and translate between them. This is going to greatly improve what you can engineer, and then you turn this into some amazing engineering artifact. And what would that artifact look like? It would look like a SAT solver. Right, so yes, there is a lot we can take from this, and hopefully Thank you.
Question?
So a couple times my attention drifted, and so but I wanted. So you may have answered this question already, but I'm dying to know. So in my mind, restarts are one of the most important parts of stat solvers. How does restarts fit into this framework of thinking? Are abstract interpreters doing something like restarts, and I haven't noticed it?
So I don't have any nice domain-based characterization for restarts. I would think of it as one of the implementation details.
No, but it's like in life you do this all the time, where you learn that like when you bicycle to work, and you learn a lesson that if you bicycle in front of a car, you're gonna get hurt. You don't have to like then bicycle a different route to learn the same lesson, right? So like this idea of like learning something, but then just restarting the search from the very beginning seems like the most important.
Throwing away what you learned, or
Yeah,
not
no,
throwing
you keep track of the conflict clauses, but then you just throw away everything and just restart the entire system from the very beginning. That's what happens quite a bit in stat solvers.
I see. I mean,
And in fact, in parallel stat, what they do is they communicate only the conflict clauses. So they actually just do totally random searching and restarting, but the conflict clauses are communicated back and forth. And without restarts, you're dead.
So, I mean, I'm not too familiar with the literature behind this, but I would say people do a lot of heuristics like this when they implement static analysis as well. You run test cases and you get certain values, and then you might use this to prune the search space somewhere, or you do seeding and things like that. Or you compute invariance, right? You use a very cheap abstract domain to compute invariance, and then you only retain the invariance, and then you run another analysis. Well, this is exactly retaining the information and forgetting actually the work that you did.
The iteration strategy is also all like that. You say, okay, I went, down one path of the code, I went down the other path, and I saw that this is all I needed. So let me throw everything that I previously explored from that point that way, and just restart everything from there and continue. I mean, and there's a big heuristic component.
The other question I have is, what about like Stallmark saturation procedure? Is there some analogous thing happening in program analysis?
Yeah, so this is work in progress, right?
Oh,
we characterize DPL, the CDCL procedure. It's a more depth-based search, and Stallmark's is more breadth-first search. But so more or less, yes, I would say that it's not just this one. Inside every SAT solver, inside every SMT solver is some abstraction and some iteration strategy sitting around, and more or less people designing program verifiers might have been doing similar things.
Yeah.
And maybe because different people have different things at their focus, they might have developed certain technology very well. Yes, please.
A major breakthrough in SAT is the use of it to combine different theories. And it uses a criticism of abstract interpretation that it doesn't accommodate theories. Does your reasoning suggest a way in which abstract interpretation can be used to get cooperating theories?
I see. So I would distinguish here between what is available in abstract interpretation tools and the theory itself. So the theory is very general. There is nothing that's not allowed by the theory. Right. In particular, the communication between theories is allowed. It may be that it's not commonly implemented, but I mean, it's definitely there in Australia and certain other tools, but maybe it's not that well known. Now, there has been a paper last year. So let me actually show you one thing. I think a good example would be suppose I have something like this, right? Very simple program. So I can analyze it using the interval abstraction, where I write A, B. So I will annotate program points like this. And if I do that, I will conclude that when I exit the program, the values of x are in the range 11 and 12. So in particular, I can conclude that I'm greater than 10. Instead, if I use the parity abstraction where I have that a variable is even, odd, or top, I will conclude that at the end, my variable is even. Okay. I cannot conclude here that the variable is not 10. I cannot conclude here that the variable is 12. But suppose I could combine the two abstract domains. I am in this interval and my value is even, then I would know that my value is 11. Okay. So this is a case of what is called the reduced product of abstract domains. Meaning I have two abstractions and I want to combine them. This was already there in the 1979 paper, but it was only mathematically defined. And in general, it's not possible to have an algorithm that's going to compute this for you. Okay? But there are special cases where you can try to find algorithms. And they have done that. So for example, here, I have a plus symbol here and I have a plus symbol here over even. This would normally not be something that's allowed in a strict sense by the Nelson-Ogden theory combination because you need disjoint signatures. But it's allowed here. So in fact, the paper from, so let me just write it here. So it's Couzeau. I hope I haven't misspelled his name. This here shows that the Nelson-Ogden theory combination is a special case of the reduced product in a very strict sense. So, if anything, it's an imprecise and definitely incorrect statement to say. So this is a thing. I guess it's a statement that's based on the available technology. From an end user perspective, it's not a mathematical statement. It's not a technical statement.
Any other?
So, in your sort of toy description of a SAT solver, the partial assignment was just an array of
Sorry, that's not a toy description.
Oh, okay.
That's Minisat 2.2. It won the competition in 2007. It's one of the best solvers out there.
Oh, okay. Well, then that makes my question even more.
An even better question.
It does.
There's an entire track devoted to this.
So the question is really, so the analogy you drew between the programs, and if you look at a Boolean program, you can see it as sort of computing a partial assignment. And so the question is it always just better to use an array of Booleans, or does it ever make sense to use sort of more complicated representations of the lattice elements?
I see. So this is an engineering question, okay? And this is why in the beginning I emphasized that it was architecture-aware engineering, and full respect for the SAT community for putting a lot of effort into this. So the Zitschaft paper talks about this. So you want to reduce the number of cache misses you're going to get when you manipulate your data structures. You want to use a data structure where the word size fits that of your architecture and things like that. So that's why they have designed it this way.
Yeah. Well, it's not purely an engineering question because when you convert.
So are you saying, sorry, just to clarify, are you saying given a fixed abstraction, are you asking what different ways to implement the fixed abstraction, or are you wanting to swap in different abstractions?
I am not sure.
Because the comment I was making was assuming you have a fixed abstraction, how would you implement it?
Okay.
Now, if you want to have a different abstraction, it's not clear that a vector of assignments is the best way to go.
Okay. I was just wondering if you might want to, if you think of it as representing a lattice element, you may think, okay, maybe I want to represent it with a more complicated formula because they're, say, exponential, so it blow ups when you go into. This
is true. So, I mean, maybe Christoph has more to say on this, but so the other big take-home message is now there are certain intuitive things that we know. So, for me, I had some questions. You can go here. Oh, this doesn't work anymore, or whatever. So, people have asked me, why do SAT solvers work? I don't know why SAT solvers work. Nobody knows why they work. There are various explanations. So, for example, there would be the complexity theory explanation where you try to do asymptotic analysis, and they have very different, not just the worst case model, you have the average case model, then you have the smoothed analysis model, and so on. So you would try to find the right model that explains why it performs well. There is the proof theory answer, which says that classic DLL can be viewed as a certain kind of tree resolution. And tree resolution with clause learning is exponentially more succinct sometimes than just tree resolution. So this is the proof theory answer. You can do a finite model theory based answer and say, well, if you have such a proof system and such an algorithm, then if you have bounded tree width or certain parameters that they've developed. So now I'm saying, well, I can give you an abstract interpretation answer, which is that the algorithm operates over an abstract domain. And there's even more to that. So here's a heuristic observation of mine that a lot of efficient things that we do in practice is based on some assumption of convexity, mathematical optimization, linear programming. Submodular functions are closely related, right? Now I can define a notion of convexity on sets of assignments using the Hamming distance. And you will see that the Cartesian abstraction represents exactly convex sets of assignments. So there's something fascinating happening here, right? So we have rediscovered some form of convexity for these things and engineered this into our solver. Yeah. So there's something bigger out there in the mathematical universe that's making things work well. And these people have discovered something like this. But you can ask the other question, why do SAT solvers not work? Do they always work? No, it's well known that there are things like the pigeonhole principle. You know, there are 5 pigeons and 4 holes, and 2 pigeons must be in 1 hole. This can kill a SAT solver, maybe not anymore. Today you can do it with 7 pigeons and 8 holes, definitely, right? But the point is, in abstract interpretation terms, my abstraction is non-relational. I cannot say X if and only if Y. This is a deeply relational property, right? If you put on your abstract interpretation lens, the answer is obvious somehow. Of course, you're using a non-relational abstraction for a relational property, poop, right? How do people solve these kind of problems? Well, they use XOR-based analysis and equality propagation. Christoph is implementing that. And when I heard that, I said, so basically, in abstract interpretation, we've done this too, right? We have equality-disequality domains, and we talk. But this gives you a new way to think about it. I'm going to have my clauses, I'm going to have my equality propagation, and then you will talk in more or less the same way abstract interpreters communicate theories. So I'm here all week, the weekends today, but thank you for coming. Thank you for